recording. There we go. All right, so from more than a week ago, we talked about how to pass parameters to a function and then how to pass a return value of scalar type back to the caller. So those were the leftover from the last time we talked about topics. And because we missed one Monday and also we have the second exam, so that's why there's like more than a week between this actual lecture and the lecture before. So I hope you guys had some time to rewatch the video from a week and a half ago, just so that you can kind of reestablish the context for this class. So what we're going to be talking about today is about the local variables, because that's the one thing that we haven't really talked about as items on the stack. So that is still a part of the caller-callee agreement. So this linked document is still going to be important. So I'm going to open it here. Right? So this is the caller-callee agreement. And the focus of today's class is on local variables. So it doesn't mean that all the other stuff is not important anymore. They're still true. Okay? So the way we push arguments from the caller's perspective, which is the last argument is pushed first, that is still true. Okay, we haven't changed that at all. The fact that we are returning a return value, a scalar type return value through register 8, that part we haven't changed. The way we call, the way we return, basically pushing the return address and then popping the return address from the function being called, that part hasn't changed. So the only thing that we are adding to what we have already talked about is where do we put all the local variables? So that's the only question that we have at this point. So the only part, because the local variables are not based on, it's not a part of the caller-callee agreement, because the caller does not know about local variables on the callee's side. So that is something that the callee alone has to deal with. So in the callee's code, the local variables are basically set up by the callee allocating additional space on the stack for the local variables, and then when it's time for the callee to return, the callee is also responsible to pop or to deallocate those local variables. So that's the only part that is not a caller-callee agreement, because it is not a part of the caller that has to know about the local variables on the callee side. So I'm going to pause here and see if there are any questions about the local variables of a C function. So are there any questions conceptually what those things are, and basically whose responsibility it is to allocate and to deallocate? Okay, seeing no questions. So what we'll do is we are going to take a look at a particular program and in C, and then we'll convert it into assembly code so that we can kind of work with it. So the way we'll do this is I'm going to locate a command line interface and then pull it to your view. And then we'll work with a sample program. All right. So we'll go ahead and revisit find max. Okay, finding a maximum of 3 variables. Well, maybe we'll just work with find max 2. And this is the .c version. So we'll do this one first. Pound include standard integer.h. Pretty typical at this point. And then we have uint8_t, find max 2, uint8_t a, and uint8_t b. And then we have a local variable, uint8_t result. And then we return result here. So this is my programming style. If I have a function that needs to return a value, I would use a local variable to store that return value most of the time, and then I will put in the return statement right after that. So this way I don't forget, to use the return value. And in between, I'm going to compute what result is supposed to be. So in this case, because we are finding the maximum, so that means if A is greater than or equal to B, then A is the maximum, otherwise B is the maximum. So if you, want to use conditional statements, this is how we can do it, but you can also use a ternary expression if you want to do it that way. So we're going to do it the kind of more regular way and do it this way, like so. So do we have any questions about find max2 as a C function? Okay, so now we go to main, and main is going to have its own local variable. So we'll call that uint8_t. We'll call this x, okay? And then we say x is find max2, and it will just ask you to find the maximum between two constants in this case. One is 45 and the other one is, say, 31, okay? And we can all do this pretty quickly in our head. The maximum between 45 and 31 is 45, okay? That's an easy one. The question is, how do we translate this program into assembly code? So that's the big question. The minor question is, how do we translate the conditional statement into assembly code? So we're going to do a V split. So I can use one side to focus on the C code and then use the other side to focus on the assembly code. Okay, there we go. So with this one, I am going to edit find max2.ttp asm. So this is going to be in assembly code. So from now on, we are going to treat main just like a normal function, which means we are going to call main from the entry point, and the main is going to have to return to this entry point here. We are also going to introduce a new way to figure out the return address. The old way is like this. Okay, so I'm going to present the old way first, and then we'll talk about the new way. So the old way is we have to use a label to designate where the return address is supposed to be, and then we decrement the stda to push the return address on the stack, and then the jmpi to the function that we're supposed to call, which in this case is main. When main returns, after main returns, this is where return address is supposed to be, and then we have a halt instruction here. So do we have any questions about this chunk of code, which is basically just regular calling and returning with no parameters, no arguments, but instead of calling some other function, we're calling main, which is not defined yet. So are there any questions about this?
No, we just got to initialize the...
Oh, the stack pointer? Can you register D? You don't really have to, but it's good to kind of show it here. Okay, very good. All right. So that means, if I want to just kind of test this code, because it's kind of good to test the code, I'm going to just have main do absolutely nothing and then just return. So main is going to be just containing the usual return code, which is ldbd, increment d, and then jmpb. So at this point, it is good to recognize, these three instructions together is returning to a caller. In most CISP architecture, and actually in many RISC architectures, these three instructions basically combine to RET as a single instruction. But in this class, I make it very explicit because I want you guys to know what is happening on the stack and how do we adjust the stack pointer in these cases. So that's the reason why, instead of a single return instruction, it is broken up into three smaller instructions just to show you how to use the stack pointer and where the return address is supposed to be stored. Okay, so make sure I save this file, and then I'm going to use the other one to try to get to riverSpider. If you have not yet set up riverSpider, now would be a good time to do it. Okay, so because it will significantly speed up your if you use riverSpider on the programs that I illustrate in the class, it will help you understand what is going on with the stack pointer, what is on the stack, when do we retrieve items from the stack, and when do we actually push items on the stack. So I highly recommend the use of riverSpider. The instruction to install that is on YouTube. I just recorded a new video to show people how to install riverSpider. So you might want to watch that if you have not yet installed riverSpider. So with that in place, I can now say, submit, and then the name of this file, which is findmax2. Oh, where is it? Why is it not finding it? I might have put it in the wrong folder. Nope, it is in the temp folder. So why is it not finding it? Nope, it's here. Findmax2.ttp is in. Okay. So using this tool, compiling, not compiling, but assembling, running, and then looking at the trace is just one easy step. So now we can go back to the assembler, and this is the correct assembler. Okay, so there we go. So we can see how this program ran. We start with the no-op instruction, then we kind of optionally initialize the stack pointer because all registers have values of 0 to begin with. And then we load the return address into register A, and then we push it on the stack. The actual last portion of the pushing is done here, where location FF is overwritten by 09, which is our return address. And then we continue execution in the function. The function has nothing else to do except to return, so it retrieves the return address back from the stack and put it into register B. We increment the stack pointer, so the stack is now balanced, and then we continue execution where register B is pointing to, which turns out to be the very last instruction of the entry code, which is the halt instruction. So this part is, is basically things that we have already talked about before the exam. So what we'll do, but it's working, okay? So the nice thing is it is working now. So with this, we're going to go back and make some more changes to the code. So now we ask the question of how do we handle local variables? And we'll start with findmax2. So now we have to implement findmax2. The first thing we want to do is to figure out what is on the stack. Well, it's going to have two arguments or two parameters on the stack. Parameter B is going to be at a higher location. Parameter A is at a lower location, followed by the return address. Oh, I forgot to mention about the trick to compute the return address. So I'm going to do it here. This is how we can compute the return address, and we don't need the label anymore. Okay, so we'll talk about this first, okay, because from here on, I'm going to use this technique so that I don't have to rely on the label to tell me where the return address is supposed to be. The dot has a meaning. So the dot has a meaning of the current location of the opcode on this line. In other words, in this case, the dot is referring to the address of the LDI instruction. Is that part okay? So the dot is always just telling me what is the address of the opcode on this line. Is that okay? All right. And then 6 plus is just saying plus 6, except it is in postfix notation. Have we talked about postfix notation in this class? Yes. Okay. So it's basically just postfix. So what we are adding is the current address of the LDI instruction, a 6, and then add them together. Okay, so basically it is just dot plus 6 in a normal infix notation. So now the question is, what is at location 6 after the LDI instruction? So the LDI instruction itself is 0 bytes away from where the dot is, because the dot is the address of the LDI opcode. The 6 as a constant is 1 byte after the dot, so the 6 is technically dot 1 plus. This would be dot 2 plus, this would be dot 3 plus, this would be dot 4 plus, but it takes 2 bytes, so that will make this one dot 6 plus. So that's how we can use the address of the LDI instruction to figure out the address of where the function or the callee is supposed to return to. All right, so I'm gonna See if you guys have any questions about this. No questions? All right. I like this technique better than the other one because now I don't need a label. Now, getting rid of a label definition is not a big deal, but without the use of labels, I cannot be using the wrong label either. Because if I need a label every time I have a call, that means I have a bazillion labels just for indicating where the return address is supposed to be. And if I use the wrong one, the program, the assembler doesn't know. Okay, the assembler will know if you use a label when you reference a label that has not been defined. It will give you an error for that. But if you have a bunch of labels already defined and you're using the wrong label, it doesn't know that you're using the wrong label. Okay, it will just kind of do weird things when the function is supposed to return. So this is a much better way of doing things. All right, so we still have the return address here because it's supposed to be returning to whoever the caller is. So now we also have the local variable, allocated here. So result as a local variable is reserved last, which means it has the lowest location. And because it is also the last thing that we are allocating, so the stack pointer should be pointing to result when everything is set up. Okay? So that means, if I'm going to define labels to tell me where I can find each item on this frame, okay, the frame is basically a collection of all the local variables, the return address, and all the parameters, then what I'm going to do is to say find max2 underscore result is defined to be 0 because the stack pointer is pointing at it when everything is allocated. And then the next thing is I would also define a label for all the local variable size. In other words, count in number of bytes. How many bytes do I need for all the local variables? Well, in this case, we only have one single local variable that takes up a byte. So that means LVS is just 1. I could have just say 1 here, but instead of doing that, I'm going to do it the long way. It's find max2 result 1 plus. Find max2 underscore result is the offset to the last local variable that I'm declaring. You guys go like, but you only have one local variable, it has to be the last one. Yes, but if I have a more complex program, I might have a whole bunch of local variables. And then the 1 plus, this 1 is referencing the size or the number of bytes that result as a local variable that, how many bytes does it need? Well, it's an 8-bit unsigned integer, it only requires 1 byte. So this 1, okay, this 1 over here is referring to the size of the last local variable. This label here is referring to the offset of where I can find the last local variable relative to where the stack pointer is pointing to. And then after that, I'm going to define find max2 underscore a, which is where I can find parameter a. So that's going to be find max2 underscore LVS. So I have to count all the local variables, all the bytes required by the local variables, and skip 1 byte to that location. That 1 plus, the 1 of this 1 plus, is referring to the number of bytes that I need for the return address itself, because I have to skip over that one. And then find max2 underscore B is find max2 underscore A 1 plus, because parameter A takes only 1 byte. So parameter B is going to be just right after that in terms of your memory space. I'm just going to pause here and see if there are any questions.
So what you're saying is that everything stores sequentially, where you can just point to this one, the result's going to be the first one, then you add the result.
Yep, because the result is here. This is 1 byte after that. This is 1 byte after the return address, and B is 1 byte after A. So they're all relative to each other. Now, do you have to define these labels this way? No, you can just define LVS to be 1, define A to be 2, define B to be 3. That works too. But if you do it that way, if you add any local variables, you're going to have to change all of them. Okay? On the other hand, if you do it this way, if you say, oh, I want to turn this into find max 3, we have three parameters. The last parameter is just going to be here, so it's not a big deal. But if you need more local variables, the rest will shift, because they're only relative to each other. So I like to do things like this, to give myself more flexibility to do the minimal editing in order to have another local variable or to have another parameter, because they're only relative to each other. Is that okay so far? So this part is more of a programming style compared to the syntax or the processor architecture. The processor architecture nor the syntax of the assembly programming language require labels to be defined this way. Okay. Unfortunately, by the time I get to the first instruction of find max2, the stack pointer is actually still pointing to the return address, because that was the last thing that was pushed by the caller before we get to the entry point of the function. So that means, the function itself is responsible to allocate and then deallocate the 1 byte that it needs for the local variable. So I could have done it this way: decrement D, reserve for result, and then increment D later on to deallocate for result. And then we have the usual return code at this point: LDB, the ST, this is increment D, and then JMPB. So I could have done it this way. The problem with this approach is, if I have more than 1 byte for my local variables, then I cannot use a single decrement and a single increment anymore. So instead of doing it this way, I'm going to do it in a much more general way. So instead of doing this, I keep it here and then I'll change it later. I will do LDIB with find max to LVS, the number of bytes that I need for all the local variables, and then subtract that much from the stack pointer. And therefore, I'm allocating for all my local variables all at once. No matter how many local variables I need, they will all be allocated in these two instructions. And then the counterpart is going to do basically the same thing, except instead of subtracting, it's going to be adding. So this part is the first part is for allocating, the second part is for deallocating. And then in between right here, then I actually have these offsets being correct. Because at this point, on line 23, where the stack point is pointing to is exactly where the local variable is. And then 2 bytes after that is where I can find the parameter A, and the 1 byte after that is where I can find parameter B. All right, I'm gonna pause and see if there are any questions about what is on the stack, relative to where we are in the instructions. Are we doing okay? Or do we have any questions about any of the stuff that I have introduced at this point? Okay, so let's just make an assumption that this is correct. Okay, and instead of doing all the complex stuff that we are supposed to be doing on this side, I just want to store, let's say 12 into local variable result, and then I halt. Okay, in other words, I just stop the entire program because I want to take a look at what is on the stack at that point. Okay. So I'm just going to put here, to do, this is just a test. So I want to store, I want result to be, 12, I said earlier. Okay, so let's see how we can do this. First of all, we have to get 12 into a register. That's pretty easy. Okay, that will put 12 into register A. Then we have to figure out where result is, okay, because eventually we want to store into that. Okay, so don't write your program like this, okay? Don't write down what I have on the projector, okay? So eventually I want B. B needs to be the address of result by the time I get to the store instruction. Okay, so the question is, what magical instructions should I use between line 26 and line 27 so that by line 28, register B has the address of result? How do we do that? We have all the labels, okay, so that means maybe we want to make use of the labels. So the first attempt is LDI B, and I need the label about result, which is find max2 underscore result, and because it's just an offset, so that means in order to get to the address, I also need to add the stack pointer to it. I want to do something like this. But this is not going to work. It is not going to work because you can only have a constant when you're using LDI. The second operand of LDI has to be a constant. In other words, it has to be a value that is resolvable by assemble time. The assembler has to be able to answer what that expression evaluates to. This expression cannot be determined at assemble time, because the value of the register D is determined at runtime, not at assemble time. So this is not going to work. Shucks. If that doesn't work here, what are we going to do? Well, how about we just do the add as a part of the instructions? So that would do it. So if I were to label this, B is basically the address of result, okay, not result 2, minus the stack pointer. That's basically what B has, is the address of result as a local variable minus the stack pointer. In other words, it is just an offset. Is that okay? Is that okay? When I said it, I was referring to the notation that register B after line 26 has an offset to get to result from where the stack pointer points to. Is that okay? Okay, all right, I'm gonna assume that it is okay. So when we add the stack pointer back to register B, what is it? It would be the same as what we had before, except we are also adding D back to what we had before. So the minus D plus D cancel out each other, so now we actually just have the address of result in register B. Well, if we have the result in register B, then we can actually go ahead and complete the assignment operation, because we just have to store register A, which already has a value of 12, to where B is pointing to, because B has the address of result. So that means now we are storing 2 local variable result. Okay, so I have no idea whether this is going to work or not, so I'll put a halt instruction here. In other words, the program stops right here. I'm not done with this program. In fact, the program doesn't even say anything about storing 12 directly into result. I'm just stashing it here to make sure that I think this will get to my local variable result. Okay, so that's just my test. Is that okay so far? And this is one thing that I recommend you guys to do, is not to write your entire program in one single swoop, okay? I can usually do it, but not all the time, okay? Most people as students in this class cannot do it, okay? You cannot just expect yourself to write the program the first time and expect it to work, okay? It is not likely to work, which is actually a good thing. Why do you think the program not working the first time is actually a good thing? So what do you do when your program doesn't work? You look for errors, you debug it, right? So you know your program has a bug, and you try to debug it. And what is the process to debug a program, particularly in this class?
Line. See what the process, just go line by line, I guess. Going line by line, just understanding what is happening, where the mistake was made.
So you're talking about manually going line by line to kind of eyeball, what the program is doing and where the flaw is.
Yeah, and
Well-
I mean, of course, there's an error that throws somewhere that I could have an idea of where the mistake was.
Yep. Now that approach is analogous of having the developer also being the tester of a program. And why does this usually not work? Okay, I'm particularly referencing, having a developer also being the person who tests a program that the developer has written. So in industry, they have developers as a team, and then they have test engineers as a separate team, and they're usually disjoint, which means they don't share people. So why do you think that is the case?
Different mindset, different approaches, or, that's pretty much it.
So the developer who might have misunderstanding of what is required of the program would have made the same assumption about how to test the program. So the test plan that is created by the same developer is unlikely to catch the bug. Is that okay? So that means we kind of need somebody else to, quote unquote, take a look at this code and see whether it's working or not. That someone else is riverSpider. Because riverSpider actually runs the code. And then you can now look at the trace and go like, am I expecting this in this register? Yep. Am I expecting this in this register? Yes. Am I expecting this location in RAM being overwritten? No. Why is this location getting overwritten instead of that one over there? Okay. That is why it is useful to have the tool that I am using right now, because you can actually track down the execution of the program line by line, instruction by instruction. Is that going to be tedious? More or less, okay? But there are techniques you can use to make it less tedious. All right, so we are going to save this code, okay, and then just run it. Now the program is not quite doing what it is supposed to, but we are expecting certain things to happen. So now the question is, what are we expecting this program to do? In other words, in terms of what is going to be put into memory, what are we expecting? So let's go back to, okay, I forgot one thing. Okay, because I forgot to actually implement this code in main, so it has the same trace as before. Because I forgot to implement the function call in main. So that's why there's nothing going on here. Okay. You go like, okay, tag, how about we put that code in here? Because main is not implemented. Okay, this find max2 is not implemented. So we'll go ahead and implement just the function call. We'll kind of forget about the local variable x in main for the time being. And all I want to do is to make the call. So LDIA 31, push it on the stack. Decrement D, STDA, LDIA with 45, same thing, decrement D, STDA, and then finally we have to get to the return address, LDIA.6 plus, okay, so this is new, okay, but it works anywhere, so STDA, that works too. So now finally we have JMPI to main, not main, find max2, and then when you get back here, I have to increment D twice to get rid of the arguments that are still sitting on the stack. Okay, so now it should work, or at least it should call the function, and we should see stuff happening on the stack. So before we go any further, I want to kind of give you guys an idea of what we should be expecting on the stack. And I got this kind of new cool toy, so we'll give it a try. Okay, so give me a second here. Yep, okay, drag it over here. All right, so this is a whiteboard, and let's see. Yep, it's connected. All right. So,
What you return, so assume that you have a function, right, and it's going to return something, and then you pass in that return to another function. During that process, do you do a deallocation or not?
So the deallocation is for the arguments.
Right.
So the arguments are pushed before you call the function.
Right.
After the function returns, you have no use of those arguments anymore. So you should deallocate the arguments right after the callee returns to the caller.
Okay. Because essentially the return is saved in the RAM, and then you're always calling to that to the other function. Is that correct?
Say that one more time?
Because the return or the result is saved or kept in the RAM, right?
In register A. The
Okay.
return value is in register A.
Right, on register A, so then you can pass it to the other function without.
Then you can push register A. So I think I get what you're asking. We can make another sample program to illustrate that one. All right, so let's go ahead and take a look at what should happen in this particular program. So we have the entry code. Okay, so let's say, this is the stack. Okay. All right, so I need to move this. It's zoom all the way out to, okay, let's zoom back in. There we go. Okay, a few more times. All right. Okay, I'm gonna undo this. Oh, I cannot undo on that side. Okay, because I just want both sides to be at 100%. Close enough. On this side, I have to turn it to 100%. Okay, so let me see if this works. Okay, I have no idea where that is. Oh, right there. Okay. I think that's good. Okay. All right. So this is the top of the stack. In other words, this is location FF. This is location FE. This is location FD. This is location FC. Whoops. FC. This is location FB. I'm just trying to count the number of bytes. I think that's all we need for now. Okay. So what is this location used for? What is that? What is the first push of the entire program? Nope. Okay, so let's take a look. Okay, let's take a look at the source code here. And can someone tell me what is the very first item push on the stack? Remember, the program always starts from location 0, okay, which means to us it is the top line of the code. The first line of the code is always the first instruction. So that means line 1. Line 1 is no op, doesn't do a single thing. And then line 2 is initializing the stack pointer. Line 3 is putting some kind of return address into register A. And then lines 4 and 5 is quote unquote pushing it on the stack. So that means, I think we should be expecting location FF to be that location that is only shown as .6 plus. Okay? I believe that is
Return of the address.
It's the return address to the entry code from main.
Right.
Okay? So we'll go ahead and kind of describe it that way. Okay, so we'll say this is the return address from main. Oops. From main to the entry code. Okay? And then what do we do? Well, we call main, so we continue execution at main. So let's go check out what main is doing. Main doesn't have its local variable yet. Okay, I haven't implemented that yet. But we push the 31 here. Okay? So that means the next thing we are doing is we are pushing 31 at this location. And that turns out to be parameter B of find max 2. And then what do? We push 45. Okay, so we have 45 here. That turns out to be parameter A for find max 2. And then what do? We have another return address on line 51. This is the return address for find max 2 to return to main. So now we also have a return address from find max 2 to main. Okay. And then what do? Well, let's see. We jump to find max 2. So now we track down, okay, find max 2, what are you supposed to do? This is find max 2, okay, so on line 9. We got a bunch of label definition. So one thing you have to remember is label definitions do not translate to any opcode or anything that is stored in RAM. Let me say that one more time. Label definitions do not translate to anything that is actually stored in RAM. So that means lines 14 to 17, they don't occupy any space, any bytes whatsoever in memory. Because labels are only constructs that the assembler itself understands. Is that okay? It is just a convenience feature for the assembler to keep track of where things are. Okay, all right. So that means the first instruction is on line 20. Line 20 says, give me the value of find max 2 LVS, which is 1, put into register B, and then we subtract that much from register B. So that means, from the picture perspective, that means register D is now pointing here. This is where the stack pointer is pointing to. Are we doing okay so far at this point? And that is our result as a local variable. So result as a local variable is right there. Do we have any questions at this point about what the stack contains and where the stack pointer is pointing to? We good? Okay. So now we shall continue. Okay. So we are done with this part here. Okay. By the time we are done with line 21, this is what the stack looks like. So what exactly is at location FB at this point? Well, it can be anything. I did not specify the value. All I did was to say, hey, stack pointer, you were pointing at the return address which the caller put on the stack. I just want you to point to the one location down. But what was at that location? Who knows? Okay, we know it's actually 0 in this case, but it can be anything. Have I stored anything into result? Not yet. So it is uninitialized. This is what happens when you have uninitialized local variable in a C program. Okay? When you declare a local variable in C in a function and you do not initialize, that local variable just picks up whatever it turns out to be at that location on the stack at the moment when the function is called. Is that okay? Now for many of us, or for some of us, we are used to scripting languages. When you say, oh, let x in JavaScript, which basically means I need to use a local variable x in this particular block, x automatically starts with a predictable value, which is called undefined. Okay? It is actually called undefined. Undefined is a ironically defined value in JavaScript. You can check for it. Okay? But in C and C++, who knows, right? Whatever memory content just turns out to be at that location before, now becomes the value of that local variable unless you initialize it. Okay, which is what the code is about to do, because the code is now about to store the 12 to B basically gets 0 because the offset to result is 0. And then when we add B and when we add D to B, it is just where the stack pointer points to, and then we are storing the 12 over at that location. So that means result is now getting a value of 12. Is that okay? So I'm expecting the stack to look like this by the time we get to the halt instruction. All right? So this is how I would write programs in this class, is to figure out what the stack should look like, what should be in the registers, and test the program gradually. Okay, just put a lot of halt instructions throughout the code, because unless you know the stack already looks like this, the rest of the code is pointless. We may be accessing the wrong location, the arguments may not be on the stack, the return address may be wrong, blah, blah, blah. So it is good to double check that the stack has the right items on it before we proceed any further in the function. All right, so now we go back to the assembler, okay, or we run it first. So we go here, okay, excuse me, go back here, say, okay, that's not what I meant to do. Okay, so I need to go back and reload the assembly code. This is called find max2.ttp-asm. There we go. Okay. And I still want to go back to this halt instruction because that's where the program ends. Okay. We are only partially done with this program. All right. So we go back to this screen and then rerun the code. Okay. So now we can go back to the assembler, and you can see that the trace is a little bit longer this time. The first location is 09. Is that the return address to the entry point code? I don't know. Not sure. So what can I do to double check to make sure that that .6 plus the notation in fact calculated the correct return address? That 09 is the correct return address from main back to the entry code. How do we check that? Which tab of the assembler should I use? The assemble tab. Okay, so we use the assemble tab, and then we say the JMP main is right here. The following instruction is where the return is supposed to go to. It is at location 09. Okay, so 09 is indeed the correct return address from main back to the entry code. Okay, so now we proceed with the analysis. We go like, okay, this is predictable. Oh, this is 1F. I think in the picture we never have 1F anywhere. Okay, let me go back to the picture where I stashed over here. Where's the 1F here? Wait, the 31 is in what base? If I say 31, it's in base 10. Oh, okay. And then the trace analyzer always uses hexadecimal. So what is the hexadecimal representation of 31? In other words, how many 16s do I need, and how many ones do I need? I need 116, right? Then we have 15 ones left, right? You go like, I don't see any 15 here. Yeah, we do. F is 15. So 1F basically means 1 of 16 and 15 of ones. Okay, 16 plus 15 is 31. Okay, so the 31 is the 1F. Okay, it is at the right location, which is FE. Then we should expect 45, which is in decimal at location FD. Okay, we know the trick now. 45 is in decimal, but we should be expecting to see hexadecimal or base 16 in the trace. So what is 45 in hexadecimal? How many 16s do we have, and then what of what is left? How many ones do we need? Let's see. 32 is the highest multiple that is less than or equal to 45, right? So 45 minus 32 is 13. And 13 is what in hexadecimal? Which digit? So you can do the counting. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, A, B, C, and then D. So 13 is D in hexadecimal. So we're expecting what? 2D to be representing the 45 in decimal. Okay, let's double check. So we go back to the assemble window and we go like, okay, what is taking the next location? Indeed, it is a 2D at location FD. We double check, this is location FD, this is 45, which is 2D. So far so good, okay? This is supposed to be the return address. FC is supposed to be the return address from find max2 to main. In other words, it should be the address of the location right after JMPI to find max2 in main. Okay, so we go back to the assemble window or the assemble tab, and then we ask, okay, so where are we talking about? We are talking about in main. We have a JMPI to find max2. This instruction is right after JMPI, so the location is 28 in hexadecimal. So we are expecting 28 to be pushed right below the 2D. So now we double check. Okay, so we go to the analysis tab again. We go like, okay, FC has 28 in it, and 28 is the correct return address. And then finally, we store the 12, a value of 12 in decimal, which is 0C in hexadecimal, to the local variable result. And according to the picture, that should go to location FB. So that means location FB should get 0C in hexadecimal. So now we go to the analysis tab, and then we double check. Okay, very good. And which one do you think the stack pointer is pointing to? In other words, what is the value of register D at this point? Register D points to the very last thing that we either pushed or reserved. And what was the last thing that we either pushed or reserved?
0C.
The 0C, okay, the location that has the content of 0C, which is location FB. So now you can look at column D and ask, what was the last time that we changed register D? It's right here. It is indeed pointing to location FB. Is that okay? This is how we quote-unquote study at this point, okay? You can look at the caller-callee agreement all day long, okay? It is all words, okay? It is kind of abstract. But when you actually run the code, you know, all the sample code that I write in this class, then you can actually see the action, right? You know, how is the stack pointer being changed? And the location that are pointed to by the stack pointer, how are those locations getting changed? So we can visualize all of that here. Now, is this a really good visualization? I would say it is sufficient, but not really good, because at any point in time, it doesn't really show you how the stack looks like. You can infer from the trace of what is on the stack and where the stack pointer is pointing to, but it doesn't give you a nice picture of, you know, something like this, you know, every step along the way. So that's one thing that you can do, is to maintain a picture like this as you go through the instructions one by one in the analysis tab. Doing that and being able to predict what is supposed to be at a location is going to help you understand all this material. Remember earlier I said, you know, it's good when your program doesn't work and force you into debugging the program, and that is actually a good way to study. Why do you think that's a good way to study? What do you do when you debug a program? Okay, let me give you two options here, okay? The first option is what I observed as a TA when I was a grad student at UC Davis. Just start making some random changes to your program and hope that one of these random changes will fix the problem. That's approach number one. Approach number two is to go line by line and use a debugger and say, by the time we get here, I'm expecting this value over here. By the time I get here, I'm expecting this value to be here. I think approach 2 sounds very tedious, but it's going to work. Approach 1 typically makes the program worse, because after a while, you have no idea what changes you have actually made in the program, so you could have made the program worse than what it was without even knowing it. And there's no way to back it up, no way to kind of restore to an earlier point, unless you use GitHub or something like that to kind of track multiple versions of your code. if you're logical enough to use revision control, you're not going to be making random changes to the code either. Okay, so that's why debugging is the best way to study the material, because it is pointing out something that you thought would work in one way, but it turns out to work in a different way. Now that can be because of one of two reasons. Okay, maybe some others too, but I typically you'll find one of two reasons. One is it is a genuine stupid mistake, which I make plenty. Okay, so those would be like, okay, I forgot to I forgot to increment d over here, or forgot to decrement d over here. It's still good to know. Okay, but typically those are fairly quick to find. It's like, okay, I forgot that. But two, it can be a conceptual misunderstanding. Oh, I thought LDA parentheses B is going to copy register B to register A. Why is it not getting the value of register B? Because what you really need is CPR AB. Load AB is going to change register A according to the memory location pointed to by register B. So the program didn't work because you thought LD is doing what CPR is doing. So that points out a misunderstanding. You go like, oh, okay. So those are two different instructions, and you just learn something. Okay, and in the debugging process, you have to not regurgitate, but you have to apply what you have learned already, just to figure out what the program should do next, and what you should be expecting in terms of memory locations and the content of the registers. So that, to me, is some of the best ways to study in a programming class, is to get some hands-on time, debug a program, and hope that your program doesn't work the first time. Because if your program works the first time, you're going to miss out a lot of opportunities to apply this kind of analysis. All right, so now that we know the program does work up to this point, we're going to finish it. So now we just go back and say, this block of code is unnecessary. I'm just testing out things, right? So you might want to jot down the timestamp, which is 11:33, okay? Just so that you know that from here on we are actually working on the code like here at this point. Okay, so we need to compare A and B. So that means we have to somehow get the values of parameter A and parameter B into registers. How about I use register A for parameter A and register B for parameter B? Would that okay with you? Is that okay with you guys? Kind of makes sense? Okay, so we'll do that. So we have LDI A find max 2 underscore A, that's the offset. Add AD, that's the address. LDAA, that's the value. I intentionally did not write down any comments here because I will give you this code at the end of the class. So you're going to get both the C code and the assembly code. What do you do with the assembly code? Start with commenting. Okay, so you can try to comment for, as much as you can remember. Okay, and if you don't remember something, it's like, I'm not sure why we have an LDAA here, then you go back to the lecture and then try to kind of listen to what I said, and they go like, oh, okay, the LDAA is supposed to end up with the value of parameter A. How does that happen, right? So you have to so the commenting process is also, a part of studying. Okay, then we can do the same thing with B. Find max 2B, add BD, LD, BB, like so. So by this time, register A has parameter A, register B has parameter B. So now I'm ready for the compare. So the compare with the if then else is always finding a reason to go to the else case. So that means I'm not really trying to confirm A is greater than or equal to B. In fact, I'm confirming A is less than B, which is the opposite of A is greater than or equal to B. Okay, so that part has to do with the compiling module, how the usual structure goes. So, but nonetheless, I did compare AB, okay, and then because I'm looking for less than, in this case it is unsigned, so it's a JCI to the else label. So the way I use the label name is tedious. Okay, I start with find max2, which is the name of the function. So this way I can have if then else in all the different functions, and I don't have to worry about the labels being overlapping, because they all have the name of the functions as a prefix. And then else 0, even though there's only one single conditional statement here, what if I want to add some more later on? Okay, so I just use a 0 here as the index to say that this is the first outmost conditional statement from the in the block of the function. Okay, and then I also define a label here. Okay, find max2 underscore else 0 is over here, but then the then branch has to jump around it. So I need a JMPI to find max2 end if 0, and then the end if 0 needs to be defined here. Find max2 underscore and if 0 has to be defined here, and I'll just comment here and say this is the else branch. Okay. In other words, I put in the entire structure of the conditional statement first, and then I go back in and go like, okay, what do I need to do in the then branch, and what do I need to do in the else branch? I worry about those later on. So it also helps to identify that, oh, okay, between the JCI and the JMPI, this is where the then branch is supposed to go. Is that okay? Now, once again, this is programming style, okay, on how we construct a program step by step. This is just a way that I find out to work the best for myself. Some people like to work on all of these things sequentially. I can't do that because I'll have to keep track of a lot of things in my head, and I really don't have a stack in my mind. So I would just kind of put everything here in the structure first, and then worry about what to do with each branch later on, which also means I need to leave notes to myself. That's what the comments are for. They are note to self. Because when the program gets really super complicated, by the time I get to an empty branch that I need to fill it in, I cannot remember what branch we're talking about, what I'm supposed to do over there. Leaving little notes to myself can help me remind myself, oh, right, this is the then branch of the conditional statement, and that one is the else branch. All right, so now we can look at the then branch and say, okay, we need to put I need to put parameter A into result, but register A has parameter A already. I'm just going to keep it there. So that means I can now work with a different register for result. And since later on I have to return result anyway, okay, I'm not going to optimize the program any further. So we'll use another register to do that. So we can now reuse register B because I don't need register B to be parameter B anymore. So I just say find max2 underscore result add BD STBA. All right, that's done. And this one is similar, but I can reuse register A at this point. Find max2 underscore result add AD STAB. Okay, by the time I get to end if, there's only one thing I need to do, which is returning result. So now I can do a LDI A with find max2 underscore result add AD. This is a LDAA, okay, because we just need to retrieve the value of local variable result and put it into register A, and we're done. Yep.
You type it on the find max2 that you asked.
Oh, next two? Okay, let's find out what happens. But thank you for pointing out the error. Making mistakes is the best way to learn. It works for everybody, including myself. So if I make a typo here and I say, let's go ahead and run this program, it's going to come back. Oh, okay, I forgot one thing. This is my favorite mistake. Everybody has some favorite operational mistake. Mine is forgetting to save the file first. You guys go like, but Tag, if you use an IDE, you would never have a problem like that. That is true, but this one I can kind of work around. All right, so there we go. The source code did not assemble correctly. Better fix the source code first. Okay, So how do I find out what's wrong with the source code? Now, I don't always have you to be sitting next to me and say, but Jack, you forgot about this, or you spelled that thing wrong. So that's why you need to go to the assembler and go to the source tab this time. Because any assemble time error is going to be reflected in column B. So here we have a few problems, okay? So we have an unresolved reference of find max without the 2 and if 0. And then we have find next to result, okay? So yes, I'm not a very good typer. But these are easy problems to solve, okay? Anything that the assembler or compiler can locate, those are not the big problems. Those are the easy ones. Okay, so I have to find out what line number. So 37 and 44. Okay, so 37 is right here. That's the one without a 2. And then 44 is max. There we go. Save the file first, and then reattempt the whole thing. All right, so the program is supposed to be done, okay? So let's check out whether it is done or not. In this case, if it is done correctly, that means by the time I get back to main, register A should really be the maximum between 45 and 31, which should be a 45, or 2D should be register A. So let's go check it out, okay? So you can always be optimistic and then figure out that it doesn't work and then try to fix it later. So it is 2D, okay? That's the last time I update register A. We got the right result. But did we clean up the stack correctly and the stack pointer getting back to 0, 0 at the very end? Yep. Did we get back to the only halt instruction, which is at the end of the entry code? Yep. So that pretty much told me the program is working 100%. Is that okay? So once again, I'm going to package up this program and along with the C code and send it to you using the announcement. And that is, quote unquote, your study material, okay? You can take a snapshot of the assembler right now if you want to, but I think you should also set up riverSpider on your own, because when you're writing code, which you will be doing in about 2 classes or so, you'll be starting to write your own code. You want to be able to debug your own code, and riverSpider, using it the way that I'm demonstrating right now, is the way to debug your program. Do we have any questions at this time? No questions? All right, so today's lab is focusing on what we have on the stack, including the local variable or variables, the return address, and the parameters. And relatively speaking, where are they on the stack? So for that purpose, I'm going to go back to my whiteboard here, and hopefully my computer left me at the same place. Okay, it is. Okay. So there's a particular name to this thing here. Okay, so let me point out what thing I'm talking about. This entire block is called a frame. Oops. I have to go back to this side and pan it like this. It is called a frame. A frame is basically the context of data that a function needs in order to do what it is supposed to do. So it would include local variables, if any, parameters, if any, and the return address back to the caller. So collectively, this contiguous block of locations on the stack is called a frame. So that name, I did not invent the name of frame. Okay, that's basically, I guess, a standard name to refer to that chunk of code in assembly language programming. Now, I haven't really finished the program yet. Okay, so I'm going to go finish now. The program is not finished because in the C code, main has a local variable x. But in this code, I have not gotten to the point yet. So I'm going to do it here. So main x, which is the only local variable, is going to be offset 0. Main underscore LVS is going to be main x 1 plus. And now I have all the labels. I can now do the allocation and the deallocation. LDIB with main underscore LVS, subtract B from D. That's how we allocate for the only local variable. And then at the very end, before we return, we also have to deallocate, which is basically the same thing, okay, the LDIB with main LVS, but this time I'm adding that much back to the stack pointer to deallocate that one single byte for the local variable. And then in here, at this point, which is after we return from find max2 and after we deallocate the 2 bytes of arguments from the stack, that's when we can do the actual store of the return value back into X. The return value is already in register A, okay? So that means I just need to compute the address of X and store the return value to X. So that means at this point, I just need an LDI. I cannot use register A because register A has the return value right now. I should not overwrite it. So I can use register B, find max, this is not find max, this is main X. Main X, that's the offset. This is the address, store to the address variable A. So that should complete the entire program. And we still got a few minutes left. So that means in this case, the stack is not going to be like this. Everything is off a little bit, because the call frame for main is now needing 1 more byte, okay? So the new frame, okay, let me pan this one first, and then I'll adjust my other one. Okay, I'll put this one at the top here. So now the stack is gonna look like this. There are 2 bytes here. That's the frame for main. There's the return address, and then there's local variable X of main. Then we have the next 4 bytes here, parameter B, parameter A, the return address to main, and also local variable result. These 4 bytes is the frame for find max 2. Is that okay? So that means the maximum between 45 and 32, which is 2D in hexadecimal, should be stored here. This should now be 2D after the entire code runs. So that means I can now try to kind of check it, okay? Make sure I save the file first, and then go back and rerun it. Now, if you don't have riverSpider, you can still trace the code execution, but it just gets a lot more painful to do it. I can show you. I think I might have shown you, but I can show it to you how to do it without riverSpider. So I'm looking for okay. Let me go back to. Let me go back to the whiteboard. I'm expecting location FE in this case to be updated to the value of 2D. So FE should be 2D. So I should be looking at column C for that particular update. And here we have it. Is that okay so far? So there are a few really important things you should be getting out of this lecture. One of those things, the conceptual stuff obviously are important, but the procedural stuff of how to use the tool that you have in order to debug your program is the other one. Okay, this is the only class teaching CISP 310, at least within this district, that uses a tool like this. All of the other classes they basically use a classic debugger where you can set up a breakpoint, but unless you set up a breakpoint, the program just executes until it either bombs out or until it's done. This is the only one class that gives you a full trace as the program executes, which I think is helpful when it comes to understanding how a program runs and how the stack is being used, how the stack pointer is being changed. All of that stuff is captured here. So that's the end of the lecture. The lab opens up automatically, but you still need the access code to get into it. And we'll go ahead and take a look. Okay, so the name is called call frame, okay, because of the name frame. And I think the access code is related to frame. It's framed. So I am going to repeat what I said a little bit earlier in the class. Your exam 2 is now graded. If you are getting a score that is low, there's still a chance to pass the class, okay? Because the final exam by itself is 40%. Can someone tell me, what is the overall percentage to pass this class with a letter grade of C or better? 37.5%. Yes. So that means somebody who would never turn in any lab, got 0 point from the first exam, got 0 point from the second exam, can kind of ace the final exam and still walk away with a letter grade of C or better, which basically means the entire class can still pass this class. Now, but for people who are not doing so well in exam 2, it reflects that they may not be understanding the instructions too well, and that's what we are doing now, okay? So that means people who did not do too well in exam 2 really need to catch up in order to do well enough in the final exam to have a chance to pass the class. And being able to come to class on time is super important. Okay, the labs contain some instructions. The reading module also contains some instructions, but a lot of the actual instructions is actually in the lecture itself. Okay, so that is important. If you need to talk to me about your grade or something like that, please come to my office hour, which is right after the lab. So I'm just going to write down the access code here. Doing well in the lab does not always translate to doing well in the final exam. Okay, so just kind of always keep an eye out on whether you're understanding the concepts or not. All right, that's all I have to say, at least the portion that I want to be recorded. So let me stop the recorder.